you remember how to go left, right, up, down, and flip? Some of you might, because you just had Algebra 2 at the end of last year, but if it's been a semester or like 2 years for you, this is something you're going to have to like rememorize, because the transformation rules are the same for every single function. So even if you took trig last year, you should have been graphing trig functions and sliding them left and right with the period. Amplifying them is stretching them or flipping them over. So even if you haven't had algebra, trig reviews all those transformation rules. I just picked 2 of the basic functions, absolute value and quadratic, but the rules are the same for any of the functions. So you can move them up, down, left, or right. So moving them up is a plus sign outside the function. Moving them down, minus sign outside the function. Remember, left and right are kind of opposites. So to move to the right, you're actually subtracting a value. And moving to the left, you're actually adding a value. I'll show you why in a minute. But if I wanted to rewrite this function, like absolute value of x plus 3 would shift the graph up 3 units. Or x squared plus 3 would shift it up 3 units. I'm just not going to write y equals every time, but y equals. So then if I want to move down, I could do like absolute value of x minus 2 or x squared minus 2. That's going to shift me down 2 units. So up or down. And when I say up, what I mean is like, you know, if you're starting here, now you're up here, up. And if you're going down, you're starting here and now you're down here, down, right? So the whole graph is shifting down or the whole graph is shifting up. If you don't know what up or down means, you might want to add that to your reference sheet. And left and right. So this is the one that seems to get students a lot, but absolute value of x, if I put a minus 1, that's shifting it to the right. So here's my original. So I've shifted to the right. And so a lot of people might be like, why? Why does it have to be a minus sign? When you plug in the number 1, 1 minus 1 gives you 0. So 1 comma 0 becomes the new x-intercept on the graph. That's how I remember it. So like the normal, right? The normal absolute value here at 0, 0. And if I take x minus 1 absolute value, and if I plug in 1 for x, I get 1 comma 0 is my output. 1 comma 0 is over here. So my new x-intercept has just shifted to the right by 1 because it was x minus 1 inside. Or you could just remember that inside these parentheses, it's that strange world where everything is opposite. So if you have x minus 1 squared, it's going to shift it to the right. And then left is just the other direction. So let's do like absolute value of x plus 5 or x plus 5 with the squared on the outside, it shifts left. So those are 4 transformation rules that you're going to want to get back under your belt. So if you just made like, you could make 4 note cards with like these 4 functions and just on the back of it write up, down, right, left, and that would help you. So this one shifted to the left, left. So up, down, left, and right. That's half of your transformation rules right there. So outside the function with a plus, outside the function with a minus, and then inside the function is your horizontal. So how many of you that rings a bell for? Does the transformation rules at least ring a bell? Yes, they're like got to be brushed off the cobwebs, but it rings a bell, I hope. Okay, and then the other 4 rules are the reflections and the stretches. So if you're flipping it completely upside down, the negative sign goes in front of the whole function. And if you're reflecting it over the y-axis, the x values are being made opposite. So reflection upside down, right? Now it's like this, upside down here. But this one, if it's over the y-axis, are you going to see a difference? So we talked about last year, if there's symmetry, basically all these x values are doing is going over here, and all these x values are going over here. So if it's already symmetric over the y-axis, it might appear to be the same. But if you look at some of our other parent functions, like the square root function, if you flip it over the y-axis, now it's going to go in this other direction. So this is not symmetrical, so you would see the reflection. And then the other two are just vertical stretches, like 2 times the absolute value or 2 times x squared is going to be steeper. And then a vertical shrink would be like a half as tall or a half as tall. And that's going to be like this. So steeper or less steep. And then we usually call this like concavity, concave up, concave down, vertical stretch, vertical shrink. So that's a lot. That is like your Bible of your 8 transformation shifts. And on your quiz, you're going to have to identify that like this goes left 5. So you're going to need to know the parent function for absolute value and that that's a left 5, and then you're going to have to graph it. So let's see, we got time. So the last thing I'd like you to end on is trying these 6 problems on the back. So refer to your parent functions, see if you can figure out the transformation rule in your head and actually plot some points. And what you might want to do is actually graph the parent function first. So like if I was going to graph the parent function on number 1, I'm going to plot the points and then just shift all those points up too. So I would do it in 2 steps. So have the parent function on the graph and have the transformation on the graph. And I will put them up in like 5 minutes with you. If this will unpause. All right, if I put the parent function on the graph first, it would be 0, 0, because the square root of 0 is 0, 1, 1, because the square root of 1 is 1, 4, 4, comma 2, and 9, comma 3. So I'm not going to connect it. That's the parent function. What a stretch does is it keeps all the x values the same, but in this case, it's going to double the height of the graph. So if I'm going to double the height of the graph, 0 doubled is still 0. 1 doubled is now 2. So I'm going to go up to 2. 2 doubled is now 4. And 3 doubled is now 6. So the x's are the steeper graph because I multiplied the height of each y value twice as tall. So when you're doing a transformation with a stretch, I would graph the parent function. And then in this case, you're doubling. Like on number 4, you're going to double and make it steeper. If it was a half, you'd actually be shrinking it half as tall. Does that kind of make sense? Maybe I'll work backwards. Did you remember how to graph the line negative x plus 3? Y equals mx plus b, right? So you start at the y-intercept of plus 3. And it has a slope of down 1 over 1, right? So that's a linear function with a slope of negative 1. Let's see, number 4, absolute value of x that's been stretched times 2. So it's just going to make your slope steeper. So I still go over 1, but twice as steep as times 2. And it normally is 2, 2, so it's going to be 2, comma 4. So your slope is now 2 in either direction instead of a slope of 1 in either direction, twice as steep. And then number 3, which way did you reflect number 3? Should have been upside down, right? Absolute value shifted upside down. That one looked good. And then let's see. This was a quadratic, number 2, quadratic that's been shifted to the right by 4, right? 1, 2, 3, 4. 1, 1, 2, comma, 1, 2, 3, 4, and 3, comma 9. 1, 1, 2, 4, 3, 9. Those are like, should be a little rhythm in your head for graphing parabolas. So all those points got shifted right 4. And then this was your cubic function shifted up to. I think I'm going to graph the parent function for myself. So 0, 0, 1, 1, and 2, 8. 1, 1, 2, 8. So there's the parent function. So I'm just going to shift all of those points up to. So up to, up to, up to, up to, and up to. So I'm connecting the X's, not the dots. Kind of makes sense. So to me, it helps sometimes to have the parent function and then do the transformation. I know on this one I didn't, but I know that parent graph by heart. So, alrighty.